Hi everyone, my name is Natalia and I'm here with Nick and Matt, and today we're going to be talking about our FPGA sort merge join accelerator. So let's start by discussing what a sort merge join is and why it matters. A sort merge join is a way databases combine two tables based on matching values. Think of it as lining up two lists, sorting them, and then merging any matching entries into a single result. This is especially important today because databases are constantly growing and datasets often become too large to fit into memory at once. The sort merge join lets us stream data, meaning we can process it but piece by piece rather than loading everything at the same time. This makes it very useful in the era of AI and big data where information is always expanding. Now let's look at the sort merge join algorithm. To implement this algorithm, you need two tables. Here they're labeled R and S, and we want to join them based on the share key, which is the zip code here. So the first step in doing this is sorting them. You sort each of the tables, R and S, by this join key. Once the tables are sorted, we then move to the merge phase. We place a pointer at the beginning of each table and we compare the current values. And then we follow these steps. If the key in R is smaller than the key in S, we move the pointer in R forward. If the key in R is greater than the key in S, we move the pointer in S forward. If the keys are equal, we've found a match, so we output the combined row and advance both the pointers. This comparison continues until we reach the end of one of the tables. This is illustrated in this picture. Our motivation for acceleration is that sort merge join is a fundamental operator in databases. Because joins run frequently and over very large data sets, even small speedups can significantly improve the system's performance. Traditional CPUs are not ideal for this workload because they are limited by memory bandwidth because data cannot be fed to the processor fast enough. They suffer from poor cache performance because database accesses patterns are irregular, and so cache data is often not reused. And they move data at the page level, which is inefficient when the algorithm only needs a few bytes. So CPUs spend more time waiting on data movement than performing useful work. FPGAs, however, address these issues directly by offering high bandwidth memory, which supplies data at a fast rate continuously. They enable streaming pipelines, which let data flow through the join logic without large buffering. They support fine-grained parallelism, which allows multiple comparisons and merges to happen simultaneously, and they enforce predictable memory access patterns.
We would start with two tables, table one, table two, and they were passed into that of HBM channel one. And what happens is that we would then go into a sort stage and we would sort specifically chunks of the table one and table two, in which we are then passing it to into the merge stage, in which we globally in which we globally combine and sort everything together. And we do that for both the entries in table one, table two. Once we do that, we take each of those entries and we would bring them into the join stage in which we would compare entries, and then we would figure out what entries to output as the result of the join. Now, to improve on this, we would do parallel sorting on smaller partitions in which we would use multiple HBM channels, not just one, in both that of the input and that of the output. We also introduced data structures for decreasing memory usage as well as increasing speed up, as I will introduce in the next slide. And we also have HLS pragmas in which standard HLS pragmas in which we are pipelining, array partitioning, and unrolling. So we introduced this new data structure called key group, and its main purpose is to help reduce memory usage and reduce the number of checks needed. So the key group is designed with a key property to represent the key value, as well as a identifier for what partition it belongs in, and the start index and the number of occurrences of this key in that partition. Now, we mainly use key group in that of the merge and join section. And in the merge and join section, we assume that we got we got a stream that's sorted already. And under that assumption, all the keys that are the same would be right next to each other. And so what we can do is we can compress them together. Basically, in this bottom left example, I have 6 zeros. And in these 6 zeros, I'm able to combine them. I'm able to combine them together into the key group data structure with a key of 0, a count of 6, and a start index of 0, assuming that 0 is the beginning of the partition. Right. And so this produces a chunk of only unique elements in that only unique keys will show up in the partition. And there's no need to look back through the chunk to get every single element of the same key, because that's what we need to do in the naive sort merge join for the Cartesian product. And gathering the occurrences of a key only takes at most k lookups from each specific partition slash chunk. And that makes it so that we can easily parallelize the operation of doing the Cartesian product. For our final architecture, we take each table and assign them 4 channels, 4 HBM channels specifically. And for each of those channels, you would read in a chunk, and that chunk is then passed into that of a local Bitonic sort, in which it's written back, and we wait until all the chunks are specifically locally sorted. Then what we would then start converting the chunks into the key groups, start compressing them down, right? And then at the merge stage, we would specifically look for the smallest element, smallest key, and then we would gather all of the elements in key groups that would also have that smallest key, in which it would be at most 4. And what we would do is we would bring it all into a join and table 2 at its merge stage would also have done the same thing, and it would bring its smallest key um, it bring its smallest key. And we would then compare and see if the keys match. If they do match, we can then start a join, right? And since the fact that the key groups data structure makes the partitions contain unique elements specifically by the key, we're able to do multiple of these comparisons and start multiple joins in which we can write out into multiple HBM channels.
So we modeled our sort optimizations in software first on ECE Linux. We used a Vivado to estimate minimum and maximum latency and to measure the area trade-offs as we added parallelism and HLS directives. So going from k equals 1 to k equals 4 gave us almost a 5x speed up in sorter latency, which makes sense because we're partitioning that table, the input tables, and sorting smaller chunks in parallel. After that, we applied targeted HLS pragmas, and the best result came from cyclic array partitioning with a factor of 8, paired with unrolling the innermost bitonic loop by 8 as well, and pipelining the copy loop. So this combination of pragmas delivered about an 8.7x improvement in minimum latency from baseline and a 3.7x improvement in the estimated maximum latency, but this comes at the cost of roughly a 10.8x increase in per sorter area.
Here we show the changes in latency and resource utilization for the merge join stage. And we can see here that in the baseline, our latency is very high, but as soon as we start introducing the key group data structure, we saw a dramatic decrease. And with some additional array partitioning and pipelining pragmas, we're able to achieve a latency that is 94 times faster than our baseline, right? And looking at the resource utilization, it makes sense that as we add more optimizations, we are using more resources. So as a trade-off to achieve 94 times speed up, this seems perfectly valid. For our initial results, we saw that as we increase the value of k from 2 to 4 specifically, we saw a increase in the speed up of the sorting phase. And it would make sense that the total resource count would go up because we are introducing more channels and more sorters, right? For the merge joint latency, because of the fact that we have more partitions now because of the increase in K, we have more overhead. But because of the fact that we have more of these channels and sorters, we also take in smaller processing sizes because we're able to distribute them distribute them more evenly throughout each of the partitions. And so it would make sense that they stay relatively the same.
Now I'm going to run the demo. So as you can see, we're in our sort merge join folder. Now to run the demo, I'll first source the FPGA script. This demo uses 8 HBM channels, 4 for each sorter. So to run it, I will just run make run target equals hardware. So as you can see, the output of our make run results in a FPGA sort time of 0.747 milliseconds and an FPGA merge join time of 3.771 milliseconds. And you can see that we ran the correct thing because there are K sorted blocks, which would equal 4, so a total of 8 HBM channels, and a partition size of 256 as our input. So now, to ensure that we have done this process correctly, we use make verify target equals hardware. So this makes sure that the outputted CSV file that we have created from the FPGA matches that of Postgres. So now I will run make verify. And as you can see, all verification checks passed.